Good morning, everyone. I am Deepika. Here is our chapter 3 Non-Aqueous Solvent. Most of the chemical reactions are carried out in solution, and the behavior of substances also depends upon the nature of the solvent. In the earlier days of development of chemistry, the reaction have been carried out only in one solvent, namely water. It has been facilitated to its by its ready availability, ease of purification, together with its favorable physical and chemical properties, such as long liquid range 0 to 100 Celsius degree, high dielectric constant 78.5, specific heat of evaporation, dipole moment, etc. Water is neutral, odorless, non-toxic, and non-poisonous. It can therefore be handled safely. The properties of water can make it an excellent and useful solvent for a large variety of substances. In fact, the excellent properties of water have hindered the development of non-aqueous solvent. The solvent other than water which are used for carrying out chemical reaction are called non-aqueous solvent. Attempts have been made to find some other substance which could behave as good solvent like water. Organic chemists have been using many solvents such as benzene, carbon tetrachloride, acetone, ether, etc. for dissolving organic compounds which are insoluble in water. Now there are many other solvents available, for example liquid NH3, H2SO4, liquid HF, liquid sulfur dioxide, etc., which have been frequently used in the present unit. We shall discuss briefly the important feature of non-aqueous solvents such as NH3 and SO2. Physical properties of solvent and their role in chemical reaction. The usefulness of a solvent is determined from its some specific properties that may help to carry out the chemical reactions and separate the products more conveniently. Some of the important physical properties of the solvent are discussed below. Number 1. Melting point and boiling point. Liquid range. The melting and boiling point of a solvent determine the temperature range within which the solvent can exist in the liquid state under atmospheric pressure. Since most of the reaction in a solvent system are carried out in liquid phase, the melting point and boiling point give the temperature range within which the solvent is useful. The melting and boiling points for some common solvent are given in table 1. Melting point and boiling point of some common solvent. Solvent H2O melting point 0, boiling point 100 degrees Celsius. NH3 minus 77.7 melting point, boiling point is minus 33.4. HF minus 89.3 melting point, boiling point is 19.5. SO2 minus 75.5 is melting point, minus 10.2 degrees Celsius is boiling point. CH3COOH melting point 16.6, boiling point 118.1. HCON CH3 twice DMF melting point minus 61.0, boiling point 153.0. H2SO4 100 degrees Celsius 10.4, 300 boiling point with decomposition. It is clear from above table that water has excellent liquid range 0 to 100 degrees Celsius at ordinary temperature and pressure. Acetic acid can also act as solvent at ordinary temperature, while NH3 and SO2 can act as solvent only at low temperature. Number 2. Heat of fusion and heat of vaporization. The values of heat of fusion and heat of vaporization also help to know the nature and strength of forces which hold the molecules of the solvent together in the solid or in the liquid state. As we know, the amount of heat absorbed by 1 mole of a substance to change from solid to liquid state is called its molar heat of fusion. Similarly, the heat absorbed by 1 mole of substance to change from liquid to vapor state is called its molar heat of vaporization. Larger the value of heat of fusion or heat of vaporization, the stronger are the intermolecular binding forces in the solid or the liquid respectively. Therefore, the magnitude of molar heat of fusion and molar heat of vaporization give us some insight into the nature and strength of the intermolecular forces, and these also determine the solvent properties. A better idea of the intermolecular forces in a solvent is obtained by the ratio of molar heat of vaporization to the boiling point. This ratio is called Thornton constant, that is delta H evaporation divided by Tb is called to Thornton constant. For normal liquids, if molar heat of vaporization are expressed in calorie and boiling point in absolute scale 0 Kelvin, then the Thornton constant has the value 21.5. If delta H evaporation are in joules, Thornton constant is about 90 for normal liquid. Such liquid exist as independent molecules without any bond between them. A higher value of Thornton constant indicate associated molecules. For example, common solvent like water, ammonia, hydrogen fluoride have Thornton constant value greater than 21.5 and are therefore associated liquid. The molecules of these liquids are polar. The association of polar molecules is due to their tendency to orient themselves so that the oppositely charged ends of the molecule come near to each other. The molar heat of fusion and vaporization of some solvent are given in table 2. Table 2. Molar heat of fusion and vaporization of some solvent water. Molar heat of fusion kg mole inverse 6.0. Molar heat of vaporization of water is 40.65. Solvent ammonia, molar heat of fusion 5.65, molar heat of vaporization 23.56. Sulfur dioxide, its solvent, molar heat of fusion 7.40, molar heat of vaporization 24.94. Solvent hydrogen fluoride, molar heat of fusion 4.58, molar heat of vaporization 30.26. The inspection of table 2 show that the values of molar heat of fusion for water and ammonia are almost same. This means that the forces which hold molecules together in water and ammonia are of same magnitude. Dielectric constant. Number 3. This property is a measure of the polar nature of the solvent and helps to estimate the solubility of polar or non-polar substance in the solvent. According to Coulombic law, the force of attraction between two charged ions is given by F is equal to Q plus Q minus divided by epsilon R square, where Q plus and Q minus are the charges of cation and anion respectively. R is the distance between them, equal to radii of the ions. Epsilon is a constant called the dielectric constant of the solvent. If epsilon is large, the force F will be small. As a result, only a small amount of energy will be required to separate the ions, and hence it will be easy to dissolve an ionic substance. Thus, in solvent of high dielectric constant, the ionic substance will dissolve readily. With the decrease in dielectric constant, the solubility of ionic compounds will decrease. The dielectric constant of some solvent are given in table 3. Solvent H2O dielectric constant 81.7 at 18 degrees Celsius, NH3 22.0 at minus 33.5 degrees Celsius, SO3 17.3 at minus 16 degrees Celsius, CH3COH 9.7 at 18 degrees Celsius, HF 83.6 at 0 degrees Celsius, HCN 123 at 16 degrees Celsius, DMF 36.7 at 25 degrees Celsius, H2SO4 100 at 25 degrees Celsius. It is clear that solvents like HF and H2O are good solvent for ionic and polar compounds because of their high dielectric constant values. On the other hand, solvents like NH3 and SO2 with small values of dielectric constant show decreased tendency to dissolve ionic compound, and especially those containing multi-charged ions. For example, carbonate, sulfate, and phosphate are practically insoluble in liquid ammonia or liquid sulfur dioxide. Number 4. Dipole moment. The dipole moment is related to the dielectric constant of the solvent. An ionizing solvent has large dipole moment and also has a large dielectric constant. It is related to the polarity of the bond in the molecule. Greater the polarity of the bond in the molecule, larger is its dipole moment. Solvents having high dipole moment have greater tendency to dissolve the polar or ionic substance. This is because of the fact that the greater polarity results in strong bond between the solvent and the solute molecule, and large solvation energy is released. This large solvation energy is sufficient to overcome the lattice energy in the solute molecules and help in dissolving the solute. Viscosity, it is a measure of the fluidity of the solvent. Solvent like water, ethyl alcohol, and carbon tetrachloride have low viscosities and are highly fluid and flow rapidly under ordinary temperature. On the other hand, anhydrous sulfuric acid and high molecular weight hydrocarbon have high viscosities and flow at much lower rate at ordinary condition. It is in solvent of low viscosities. The operations such as precipitation, crystallization, filtration, etc., can be easily carried out without any difficulty. With increasing the viscosity of a liquid increases the difficulty of such operation. Types of solvent. Non-aqueous solvents have been classified in many ways. The following are the important classification based upon the chemical properties of the solvents: protonic and non-protonic solvent, acidic, basic or amphiprotic solvent, ionizing and non-ionizing solvent, coordinating and non-coordinating solvent. Number 1. Protonic and non-protonic solvent. The solvent from which proton can be derived are called protonic solvent. Therefore, protonic solvent contain ionizable hydrogen H+. Common example are H2O, HF, H2SO4, HCN. The solvent from which proton cannot be ordinarily derived are called non-protonic solvent. These are also called aprotic solvent. In other words, these solvents do not contain ionizable hydrogen atom. Common example are liquid SO2, N2O4, C6H6, CHCl3, CCl4. Number 2. Acidic, basic or amphiprotic solvent. This classification is based upon the acidic or basic behavior of solvent. The solvent which have a strong tendency to donate proton are acidic in nature and are called acidic solvent or protogenic solvent. For example, H2SO4, liquid hydrogen fluoride, acetic acid, CH3COH, etc. Solvent which have strong tendency to accept protons and are basic in nature are called basic or protophilic solvent. For example, liquid ammonia, pyridine, hydrazine, ethylenediamine, etc. The solvent which neither have a strong tendency to gain nor a strong tendency to lose protons are called amphiprotic or amphoteric solvent. In other words, they neither behave as strong acidic or nor basic but can behave as acidic as well as basic depending upon the nature of the reacting species. For example, water, ethyl alcohol, methyl alcohol, etc. Ionizing and non-ionizing solvent. The solvent which are capable of undergoing self-ionization are called ionizing solvent. Some common examples are H2O, NH3, HF, SO2, N2O4, ClF3, BrF3, PoCl3, etc. This ionize as shown below. H2O plus H2O gives H3O plus OH minus. NH3 plus NH3 gives NH4 plus NH2 minus. HF plus HF gives H2F plus F minus. SO2 plus SO2 gives SO2 plus SO3 2 minus. N2O4 gives NO plus NO3 minus. ClF3 and ClF3 gives ClF2 and ClF4 minus. PoCl3 and PoCl3 gives PoCl2 plus PoCl4 minus. These solvents are generally polar or ionic in nature. On the other hand, the solvents which do not ionize at all are non-ionizing solvent. Some common examples are benzene, carbon tetrachloride, hydrocarbons, etc. These are non-polar and non-ionic in nature. Coordinating and non-coordinating solvent. The solvents which are capable of coordinating with the metal ions or anions of the solute are called coordinating solvent. For example, NH3SO2 dimethyl sulfoxide, acetonitrile, dimethyl formamide, nitromethane, etc. On the other hand, the solvents which are not capable of coordinating with the metal ions or anions of the solute are called non-coordinating solvent. For example, CCl4, saturated hydrocarbons, etc. These are not of much interest to inorganic chemists. Practice problems. Classify the following non-aqueous solvent as protic or aprotic. HF, PoCl3, CH3, CH2OH. Answer. HF, H2SO4 and CH3, CH2OH are protic solvent. What are amphiprotic solvent? Give an example. The solvent which neither have a strong tendency to gain or nor a strong tendency to lose protons are called amphiprotic solvent. For example, water. Which of the following statements are correct? CHCl3 is non-ionizing solvent. The ratio of heat of vaporization and the boiling point of the liquid is called dielectric constant. The solvent NH2, CH2, NH2, C6H5, N2H4 and N2O4 are all basic solvent. The larger the dipole moment of a solvent, the smaller will be its ability to dissolve polar substance. The solvent HF and H2O are good solvent for ionic and polar substance. Answer: CHCl3 is non-ionizing solvent is correct statement. The solvent HF and H2O are good solvent for ionic and polar substances is also a correct statement. Types of reactions in non-aqueous solvent. The following types of reaction commonly occur in non-aqueous solvent. Number 1. Metathetical or precipitation reaction. The reaction in which precipitation occurs on mixing two solutions are called metathetical or precipitation reaction. These types of reaction can be predicted if the values of the solubility product of the compound formed in the solvent are known. These values depend upon the nature of the solvent used. For example, in water, silver nitrate and barium chloride react to give a precipitate of silver chloride, leaving barium nitrate in the solution. 2AgNO3 plus BaCl2 gives in reaction of water 2AgClPpt plus BaNO3 twice. On the other hand, in liquid ammonia, a precipitate of silver chloride combines with barium nitrate to give precipitate of barium chloride, leaving silver nitrate in solution. 2AgCl plus BaNO3 twice react in liquid NH3 gives BaCl2PPT plus 2AgNO3. Therefore, reversal of a chemical reaction takes place on changing the solvent. Similarly, sodium hydroxide is highly soluble in water, but it can be precipitated in liquid ammonia. Water-soluble copper sulfate may be precipitated in anhydrous acetic acid. Salt formation. Number 2. The reaction between appropriate acidic and basic substances to form salt are called salt formation reaction. In such cases, the solvent used must be one in which the appropriate acid and base can exist. For example, sodium uride cannot be prepared by the reaction of urea on sodium hydroxide in water. It is because the strong base available in water will not take a proton from urea molecule. In other words, the sodium salt of urea is unstable in water and uride ion will take a proton from water to form hydroxide ion. Na plus NaCONH2 sodium uride plus H2O gives Na plus OH minus plus NH2CONH2 urea. However, this salt can be easily formed in liquid ammonia solution by the reaction of urea with strong base sodamide. Urea plus sodamide in presence of liquid NH3 gives Na plus NHCONH2 sodium uride plus NH3. Number 3. Acid-base reaction. The acid-base reaction in non-aqueous solvent can be explained on the basis of solvent system concept as already learnt according to solvent system concept. An acid is a substance that by direct dissociation or reaction with the solvent gives the cation characteristic of the solvent. Similarly, a base is a substance that gives the anion characteristic of the solvent. The acid-base behavior of a substance depends upon the acid-base nature of the solvent, the character of the solute, and the solute-solvent interaction. In the case of protonic solvent, cation is the solvated proton and the Bronsted protonic concept is same as the solvent system concept. For example, in liquid ammonia solvent, NH4 plus ions act as acid and NH2 minus ions act as bases. The neutralization reaction is NH4Cl acid plus NaNH2 base in presence of liquid NH3 gives NaCl salt plus 2NH3 solvent. In non-protonic solvents such as benzene, carbon tetrachloride, Lewis acid-base type of reaction can occur because of non-ionization of solvent. The acid-base behavior of a solute in a solvent depends upon the acidity or basicity of the solvent. For example, acetic acid behaves as strong acid in ammonia, weak acid in water, but a base in sulfuric acid. CH3COH strong acid plus NH3 gives CH3CO minus plus NH4 plus. CH3COH weak acid plus H2O gives CH3CO minus plus H3O plus. CH3COH plus H2SO4 gives CH3COO H2 plus HO4 minus. Number 4. Solvelytic reaction or solvolysis. The reaction in which the solvent molecules react with the solute in such a way that the solvent molecules split up into two parts, one or both of which get attached to the solute molecule or ion, are called solvolytic reaction. Since these reactions occur through self-ionization of the solvent, the concentration of either the cation or the anion is changed. For example, the solvolytic reaction in water, ammonia, and ethanol are given below. Water as solvent, 2H2O plus 2H2O gives H3O plus OH. Autoionization, SO2Cl2 plus 4H2O gives SO2OH twice plus 2H2O plus 2Cl negative. Concentrated of H3O plus is increased. Concentrated of OH minus is increased. Ammonia as solvent, 2NH3 gives NH4 plus NH2 minus. Autoionization, SO2Cl2 plus 4NH3 gives SO2 NH2 twice plus 2NH4 plus 2Cl. Concentrated of NH4 plus is increased. H plus H minus plus NH3 gives NH2 minus plus H2. Concentrated of NH2 minus is increased. Alcohol as a solvent, 2C2H5OH gives C2H5OH2 plus OC2H5 minus. Autoionization, SO2Cl2 plus 4C2H5OH gives SO2OC2H5H2 5 twice plus C2H5OH2 plus 2Cl minus. Concentrated of C2H5OCOH2 plus is increased. CH3 plus C2H5OH gives OC2H5 minus plus. It may be noted that in case of solvent like water, ammonia, alcohol, acetic acid, etc., the terms hydrolysis, ammonolysis, alcoholysis, and acetolysis are used respectively. Solvation, the reaction in which the molecules of the solvent get attached to a solute species, cation, anion, or molecule, are called solvation reaction. The species formed is called solvate. The solvation reaction in water, ammonia, alcohol, etc. are called hydration, ammoniation, alcoholation, etc. and the resulting solvates are called hydrate, ammoniates, alcoholates, etc. For example, CSO4 plus 4NH3 gives CSO4.4NH3. Ammoniate, COCl2 4H2O gives CuH2O4 whole twice plus 2Cl minus. Hydrate, BaSO4 plus 3H2SO4 gives BaSO4 dot 3H2SO4 solvate of sulfuric acid. Solvation of a cation occurs through ion dipole interaction between the positive cation and the negative end of the dipole, or through coordinate bond in which the solvent molecule donates a pair of electrons to the cation. On the other hand, solvation of anion occurs through ion dipole interaction between the cation negative ion and the positive end of the solvent dipole, or through hydrogen bonding in case of solvents such as water, ammonia, or hydrogen fluoride. It may be noted that in certain cases it is difficult to distinguish between solvation and solvolysis because in many solvolytic reactions the first step consists of solvation reaction. However, the term solvation is used for those reactions in which the solvent molecules remain in the resulting product. Let us discuss some reaction in two common non-aqueous solvent. Liquid ammonia. Liquid ammonia is one of the most extensively studied non-aqueous solvent. It is now used as a highly useful solvent and a reaction medium for many types of organic and inorganic synthesis. Its most of the physical properties resemble those of water as in given table 4. Property: ammonia, water. Freezing point minus 77.70. Boiling point minus 33.3800 degree. Density 0.68 at minus 303 at minus 333.3, 1.0. Dielectric constant 22.0 at minus 33.5 degrees Celsius, 78.5 at 25 degrees Celsius. Viscosity centipoise 0.254 at minus 33.5 degrees Celsius, 0.959 at 25 degrees Celsius. Specific conductance ohm inverse centimeter inverse 2.95 into 10 raised to power 7 at minus 35 degrees Celsius, 6 into 10 raised to power minus 8 at 25 degrees Celsius. Dipole moment 1.47, 1.85. Heat of fusion 0.018 ammonia, 0.20 water. Heat of vaporization 23.6 ammonia, 40.7 water. Comparison of properties of liquid ammonia in water. The comparison of properties of liquid ammonia in water reveals that the following points. Liquid range. The melting and boiling point of liquid ammonia are lower than those of water. In liquid ammonia, the liquid range is from -77 to -33 degrees Celsius. Therefore, it presents some handling problems. Therefore, some precautions have to be taken while using liquid ammonia as a solvent. It is generally handled in cooled vessels, and nowadays a wide range of techniques have been advanced for handling it. Hydrogen bonding. Like water, liquid ammonia is an associated solvent through hydrogen bonding because it contains a strongly electronegative element nitrogen. However, ammonia molecules are less strongly associated because nitrogen is less electronegative than oxygen and therefore N bond is weaker than OH-O bond. As a result, the freezing point and boiling point of ammonia are less. Since ammonia is less associated than water, it is better solvent for organic compound. Dielectric constant. The dielectric constant of ammonia is lower as compared to water, suggesting its lower tendency to dissolve ionic compounds. Liquid ammonia is therefore a poor solvent for ionic substances. Soluble salts include most of ammonia salt, nitrate, thiocyanate, and iodides, fluorides, and many oxide salts are generally insoluble. However, ammonia has lower viscosity than water, and this might be expected to promote greater ionic mobilities and thereby compensate to some extent for the effect of dielectric constant. Number 4. Self-ionization. Both ammonia and water show comparable self-ionization as represented below. 2NH3 gives NH4 plus ammonium ion plus NH2 minus amide ion. 2H2O gives H3O plus hydronium ion plus OH minus hydroxyl ion. However, the extent of autoionization of liquid ammonia is less than that of water. This is clear from its low specific conductance and lower ionic product. KNH3 is equal to NH4 plus NH2 minus is equal to 1.9 into 10 raised to power minus 23 at minus 50 degrees Celsius. KH2O is equal to H3O plus OH minus is equal to 1 into 10 raised to power minus 14 at 25 degrees Celsius. Therefore, ammonia can conduct electricity to a feeble extent. Ammonia as a better solvent than water. The following properties of ammonia make it a better solvent than water. Liquid ammonia is a very poor conductor of electricity. The specific heat of ammonia is more than that of water. Liquid ammonia is less viscous than water. Most salt, when dissolved in liquid ammonia, conduct electric current better than in water. This is not due to ionizing power of ammonia, but due to low viscosity, which greatly increase the mobility of the ions. Liquid ammonia has high critical temperature and pressure. It is less associated than water and therefore is a better solvent for organic compound. Liquid ammonia forms strong reducing metal ammonia solution with alkali metal. Therefore, it is an excellent solvent for many reduction reactions in liquid ammonia. As mentioned earlier, ammonia has water-like properties as a solvent. It is therefore expected that the reactions which take place in aqueous solution can also occur in ammonia solution. Some of the important chemical reactions occurring in liquid ammonia are given below. Acid-base reaction. Number 1. The acid-base reaction or liquid ammonia can be easily understood by comparing the reaction in water. 2H2O gives H3O plus OH minus. According to solvent system concept of acid and base, the substances producing H3O plus ion in water act as acid while those producing OH minus ions act as bases. Liquid ammonia ionizes as 2NH3 gives NH4 plus NH2 minus. Therefore, the substance producing ammonium ions NH4 in liquid ammonia behave as acid while those producing amide ions NH2 minus behave as bases. For example, ammonium salts such as ammonium halides, thiocyanate, nitrate are soluble in liquid ammonia and behave as as acid. NH4Cl in liquid NH3 gives NH4 plus Cl minus. Similarly, imide and nitride behave as bases in liquid NH3. The commonest base in liquid ammonia is potassium amide, which ionizes as KNH2, liquid NH3 K plus NH2 minus. Lithium amide, sodium amide, and alkaline earth metal amides have a very low solubility and therefore KNH2 is the commonest base in liquid NH3. Proteolysis. Certain compounds like urea, acetamide, sulfamide, etc., which are incapable of donating proton to water, can readily donate proton to NH3 in liquid ammonia. These reactions are called proteolysis reaction. Hence, these compounds act as acids in liquid ammonia.